Hi Doctor, I'm TEONG. So today and right now, I will do this assignment 1.1, which is to explain the example 9.2 in the reference book, Fundamentals of Machine Elements, 3rd edition. So let us read the question first. A column has a square tubular cross-section. The wall thickness is 10 mm and the column length is 12 meter. The column is usually loaded in compression and has pin ends. The mass of the tubular column must not exceed 200 kg. In this question, we need to find the material that is shown in the table 3.1 that will give the highest buckling load. And then we calculate the critical load. So now let's collect the data from the question, which is this. And this is the table 3.1 as mentioned in the question. And this is the step flow that I have learned in this chapter. First, we need to identify the data and info, and then we need to decide whether to use Euler or Johnson equation to solve this question. When the slenderness ratio, as known as C, is bigger than the critical slenderness ratio, which is CC, then we should use the Euler equation. Otherwise, we use the Johnson. After we have decided to use which equation, then we can start to calculate. But in this question, it didn't show any info about the H, which is the width of the tubular, the column. So we need to find H first, as the question has give the mass. So maybe we can find a clue over there. Let's see. First, we need to identify the moment of inertia for the square tubular, which is this formula. And then it is a pin ends. So the effective length, the LE, is equal to the L. And this is the calculation. Let's start. We know that the rho, which is the density, is equal to M over V. And then from the V, we can derive it by substitute the area of the square tubular into it. And then we will form an equation 1. For the moment of inertia, actually we can simplify it. After we have simplified it, we can substitute the equation 1 into it, and then it will become this equation. So for the critical load, we can substitute the equation that we have derived into it, and then we can create a critical load with a a little bit different equation. From this equation, we can find a clue, which is a relation between the critical load with the modulus of elasticity and the density. And from this equation, we can know the relation. Now we can determine the material that will create the highest buckling load among all the materials in the table 3.1. Now, I will using the Microsoft Excel to calculate the ratio of E over rho, and then we can determine to use which material to calculate the buckling load. So this is the table. First, we can realize that the aluminum alloys actually has given a range of the density. So actually it's quite difficult for us to determine the ratio. So on the next slide, I will Google the info about the aluminum alloys and then calculate the ratio. And then another point is the magnesium. For the magnesium value, I Google it also and sum into it, because in the table 3.1 it didn't show the value for the magnesium. It only shows the value for the magnesium alloys. And then we can realize that the steel, the high speed steel, actually is the highest ratio, which is 0.0270. So in this section, I will explain it at the problem section. So this is the value for the aluminum alloys. I've calculated, and still we are going to use the magnesium value as shown in the example, because it will give a higher buckling load. We will see it in the result section. So for the calculation, we found the H first by using the material we derived just now. So after we have found the H, then we can calculate the PCR, which is the 282 kilonewtons. So in this question, in this example 9.2, we can see that the question didn't use any method to decide to use Euler or Johnson. So now we will verify it. So right now we will calculate the I, the A, the slenderness ratio, and the critical slenderness ratio. And for this result, we can see that the C is bigger than CC. So the Euler method is used correctly. And this is the reference that I used to explain this example. So the search engine that I use is Google. So there are a few problems that I found in this question. First will be the aluminum alloys. Yes, it is only given a range of data, but didn't specify it out. So I Google it by myself and calculate it. Second, the magnesium that shown in the table 3.1 is magnesium alloys, but not the magnesium as shown in the example 9.2. So of course, same. I Google it, the magnesium value, and calculate it by myself at the same time. And it gives us the value of 0.0259 ratio. But the most confused part is about the ratio that I calculated in this list. There's one highest ratio I found, which is the steel with high speed, which is 0.0270, higher than the magnesium. But why the example didn't use it? So I recalculate it again. I calculate the H and calculate the PCR again for the steel, and then here's my calculation. I calculate the H and I calculate the C and CC. So we can see that the C is bigger than CC. We can use the Euler equation to calculate this column. And the critical load that I calculated is the PCR, which is 14.9 kilonewtons. Even though the E over rho ratio for the high-speed steel is higher than the magnesium, but it gives out a lower critical load compared with magnesium. This is due to the H value that calculated. The density will affect the H value, thus affect the PCR value. So the PCR value will not just affected by the ratio of E over rho, but also the H2. So that's why in the example 9.2, they use the magnesium value to calculate the critical load, but not the high-speed steel. So that's all for me. Thank you, Doctor. I hope that my explanation is clear enough for you, and hope that I didn't make any mistake and clarify enough. Thank you.